Welcome to Chapter 12. Quick note before we begin this lecture, we are going to have another exam on Friday. The exam will follow the same structure as last time. I'm going to shoot for around 40 to 50 questions, again, about 80 minutes. And again, you'll have from noon Friday to 6 p.m. on Saturday. All right, with that said and that out of the way, let's get on with it. Got a lot of slides to go through today, but sort of even more conceptual than yesterday. There's a couple calculations we're going to use. We're going to look at what makes liquids liquids, what makes solids solids, and what are intermolecular forces. If you read into the title there a little bit, you might guess that they are the forces between molecules. Most of our tastes originate from the interactions between molecules, specifically molecules and receptor cells on our tongue. And the way that our tongue detects different types of molecules, right? We know that sucrose or sugar is sweet. Is that there's a molecule in your tongue that makes up the receptor. And that receptor has a slot in it that fits sucrose molecules. And so every time you're drinking something and you taste something sweet, those sucrose molecules are locking in with those receptors on your tongue to detect sweetness or other flavors as well. The specific interaction between the molecules in coffee that tastes bitter and the taste receptors on the tongue is caused by intermolecular forces, attractive forces that exist between molecules. Intermolecular forces are essential for many physiological processes, just like taste. Less specific intermolecular forces exist between all molecules and atoms. The intermolecular forces are responsible for the very existence of liquids and solids, right? Because as we talked about, gases, we assume, and it works most of the time, right? We can make this assumption that most of the time there are no interactions between the individual molecules. So the physical state of a sample of matter depends on the strength of the intermolecular forces relative to the amount of thermal energy. All atoms are in constant random motion that increases with increasing temperature. The energy associated with that motion is called thermal energy. Substances with weak intermolecular forces relative to thermal energy are more likely to be gases. If the intermolecular forces are strong relative to thermal energy, the sample will likely be liquid or solid. So those strong forces then, if those forces are strong relative to this thermal energy, this motion of the atoms, it will hold them together, right? So it can fight back and it can overcome that thermal energy to hold the atoms and molecules close together. In gases, molecules or atoms are separated by large distances, and this large distance is part of what makes the intermolecular forces so weak. In solids and liquids, the molecules or atoms are touchingly close, so they're all very, very close to each other, especially relative to gases. The difference between solids and liquids is in the freedom of movement of the molecules or atoms. In liquids, and we talked about this, I think in the first week, in liquids, the atoms or molecules, they're free to move around each other, but they're still within touching distance. In solids, the atoms or molecules are in their fixed positions, or are in fixed positions, but although thermal energy causes them to vibrate about a fixed point. So they have their spot and they have their place, but they vibrate inside of that area. So you see gases, right? They're free, they're flying around, they're free spirits. We have liquids, they're a little more social. They like to stick together a little bit more. They like to be nearby, but they don't like to be too held down. You know, they still like to move around the group. They like to mingle. Solids are more, they're very rigid. They're very strict. They have their specific rows and their lines that they sit in. That's where they want to be, and they stay there. Low densities. Sorry, these are properties of gases. So gases, in comparison to liquids and solids, have very low densities. And this makes sense, right? If the atoms and molecules inside liquids and solids are within touching distance, they're very close together. So we have a lot of mass in a small area. That means they have higher densities. Whereas gases have lots of space in between the individual atoms or molecules that make up the gas. And so they have low density. They have their mass spread out in a large volume. Gases also have indefinite shape, right? We talked about smells that might be wafting from the kitchen, or if you open your window, you get smells that come in from outside, or there can be other more unpleasant smells that can spread. So they have this indefinite shape. They assume the shape of their container, and they have indefinite volume. So they'll spread out, but they can also be compressed because we can take that space in between those atoms and molecules and we can shrink that. They have weak intermolecular forces relative to thermal energy. So if they do get close to each other, or if they do bump into each other, they just bounce off or pass right by with very, very little interaction. Carbon dioxide gas is an example of this, right? It's a gas. Liquids, on the other hand, have high densities in comparison to gases. Again, they're in touching distance, so the atoms and molecules are very close together, so we have mass in a small area. Lots of atoms and molecules in a smaller area. They also, like gases though, have an indefinite shape. Those atoms and molecules can move around each other, so they assume the shape of their container. But unlike gases, they have a definite volume. So they are not easily compressed. And in fact, most of the time we consider them to be uncompressible. So that's why hydraulic fluid systems work. You can push fluid through a hose or a tube and it transfers that energy, it transfers that force from one end to the other. They have moderate intermolecular forces relative to thermal energy. They're still able to move around each other, but not like solids. So liquid water would be an example of a liquid. Solids now are our most dense type of matter. They have high densities in comparison to gases again. Density of solids, not necessarily higher than that of liquids, but most of the time it is. Definite shape, right? They don't assume the shape of their container. They have their own shape. When you set your, phone on the table, it doesn't drip off the table. They have a definite volume. So again, they're not easily compressed. Otherwise, when you sat on a wooden chair, the chair would just bend. A lot of things wouldn't work if they did not have a definite volume. And we do have solids that can be compressed, right? If you have a memory foam mattress, different property taking place there. That's more like elasticity. And our solids may be crystalline or they may be amorphous. So if you have a crystalline solid, it's very ordered, whereas amorphous is very disordered. But those molecules have strong intermolecular forces relative to thermal energy, which keeps them in their respective positions. Table sugar being one example of a solid. Liquids, right? They assume the shape of their container. So if you fill up a beaker with water, they will form to that beaker. In a solid, such as ice, we've now taken our liquid water and frozen it. We've taken that thermal energy out so that the molecules are moving around less. They become fixed in place. They still vibrate at their fixed point, but they don't break out of that fixed point to become liquid. Without intermolecular forces, solids and liquids wouldn't exist, and everything would be gaseous. Liquids also have surface tension and viscosity, which are a result of intermolecular forces. If you've ever seen or filled up a water glass so that it just bubbles over the top, that's surface tension. And viscosity is the thickness of a liquid. If you're familiar with engine oils, those have varying viscosities for different engine specifications. Honey, though, is a very familiar viscous liquid, right? So it's a high viscosity, means that it doesn't flow very well, or very quickly, I should say. You can take a paper clip and it'll float on the surface of the water if you place it there carefully enough. And that is because it's held up by surface tension. So this surface tension is the tendency for liquids to minimize their surface area. gasoline doesn't have this same property because of the different type of intermolecular forces. Those forces are weaker, and so the surface tension can't hold up the paperclip, and the paperclip will just fall into the gasoline. Surface molecules experience a net inward force that creates tension at the surface and resists penetration. So those intermolecular forces between the molecules holds them together. Not so much that they can't move around still, but it does prevent things from entering the liquid. It's called surface tension. Water drops are spherical because of surface tension caused by attractive forces between water molecules. It's trying to minimize its surface area, and the smallest amount of surface area is a sphere. So if you take water, and there are plenty of videos of this, people on the International Space Station taking water, without any gravity, you get floating spheres of water. And if you have a towel, and you take that towel and you wring it out, it was Chris Hadfield saw him do this one on YouTube. If you take that wet towel and you wring it out, instead of that water dripping away, it moves up and onto your hands because there's no gravity to pull it away from your hands, and it's trying to minimize its surface tension by spreading out on your hand, or minimize its surface area. Viscosity, like I mentioned, honey, right? Honey is a viscous liquid, is the resistance of a liquid to flow. So liquids that are viscous flow more slowly than liquids that are not viscous. For example, motor oil is more viscous than gasoline, if you've ever changed your own oil. Excuse me. And honey is more viscous than water. Viscosity is greater in substances with stronger intermolecular forces, because the molecules can't move around each other as freely, which hinders the flow. Maple syrup is another viscous liquid, and it's more viscous than water because its molecules interact strongly, and so cannot flow past one another easily. And we'll talk about what these intermolecular forces are. Evaporation, or vaporization, is a physical change in which a substance is converted from its liquid state into its gaseous state. The rate of vaporization increases with increasing surface area, increasing temperature, and decreasing strength of intermolecular forces. So you can think about if you take water and you spray it out onto your back patio in the winter, or let's say you have a glass of water. If you leave that glass of water in the winter, has a small surface area, and you leave that out, it'll take a long time in the winter for that glass to completely evaporate and be empty. If you put that out in the summer, like we are now, although it's fairly cool out now, if you put that out in the summer, we're increasing that temperature, and that water will evaporate or vaporize faster. Even faster is if you were to take that same amount of water and pour it out on the sidewalk. Again, in the winter, when the temperatures outside are relatively cool, that evaporation happens much more slowly, and that's why things tend to stay wet in the winter. In the summer, however, if you pour that out on the sidewalk, it pretty much vaporizes immediately here in Fresno because it's so hot. There's more energy that gets transferred to the atoms of the water so that they can break those intermolecular forces, or break away from those intermolecular forces and become gases. Decreasing strength of intermolecular forces is related to the type of molecules that we're working with. So liquids that evaporate more easily are termed volatile, while those who do not vaporize easily are termed non-volatile. Good test question right there. Definition, true-false question for the definition of volatile. Evaporation. Sorry. We're still talking about evaporation, not condensation. Molecules on the surface of a liquid are held less tightly than those in the interior. The most energetic molecules can break away into the gas state in a process called evaporation. And if you give these gases, or these molecules, more energy, then they are more able to break away and evaporate more quickly. At a given temperature, a sample of molecules or atoms will have a distribution of kinetic energies. Only a small fraction of molecules has enough energy to escape. So if you look at this chart down here, and maybe I should finish reading this. At a high temperature, more molecules have enough energy to escape. So let's zoom in on this graph. And just like this graph shows, if we have a low temperature, we have a distribution of energies for different molecules. So you'll have a few molecules who are down here at the bottom end, very, very low energy. They're moving very slowly. And then as we increase in kinetic energy, you'll start to see more and more and more. And this average, this peak here, or actually the average of all of these temperatures, so really more like maybe right here for the blue. Let's grab a blue marker. So we're like in here for blue, maybe. This will be your temperature of the room. And then as we increase up this kinetic energy curve at this particular temperature, we see fewer and fewer atoms who are high energies at these energy levels. And then there's just a few up here who have enough energy to escape into the gas phase. So if we delete all this and then instead we look at this higher temperature, you'll see that again, right? There's still a lot of molecules and atoms who have the same amount of energy as we did at this lower temperature, but our distribution has shifted, and you see that it's gotten shorter than our lower temperature. So that distribution, as we go to higher temperatures, starts to spread out. And as it spreads out, we get more molecules that are in this high energy region as compared to the ones that are just in the low temperature. So we get more and more molecules that are able to leave into the gas phase. You can go more into that if you want. There are definitely resources that you can find if you take higher levels of chemistry after this. You'll talk about those. But for this class, we're just kind of talking about a lot of the general concepts for these things. We will have a few calculations that we'll go over, though. Condensation now is a physical change in which a substance is converted from a gas to its liquid state. We talked about evaporation, and so evaporation and condensation are opposites, where evaporation is liquid leaving into gas, condensation is a gas becoming liquid. When the rates of condensation and evaporation become equal, a dynamic equilibrium is reached, and the number of gaseous water molecules above the liquid remains constant, because we constantly have a set of, let's see if I can sort of draw something here. We have as many, we'll use the black here, we have as many molecules leaving and evaporating as we do as molecules condensing. I'm not sure if I drew exactly the same number there. I think I did. And so that's called a dynamic equilibrium. There are still atoms leaving, and then there's still atoms condensing and staying. So we have evaporation and condensation, but at the same rate. So it's like if you poked a hole. Well, it's like if you had somebody adding cups of water to a bathtub and somebody removing cups of water from a bathtub. If you're doing it at the same speed, you're never going to have more water in the bathtub or out of the bathtub. The vapor pressure then is the vapor pressure of a liquid is the partial pressure of its vapor in dynamic equilibrium with its liquid. So that's what we talked about yesterday when we talked about the vapor pressure of water. That vapor pressure of water is dependent on the temperature. So if we go to higher temperatures, we have more water that stays in the gas phase. If we have low temperatures, we have more water that stays in the liquid phase, and we get different vapor pressures because of that. So here we've just added this water in, and we've put the cap on it, plugged it up, and we begin to have these water molecules leaving into the gas phase. And as we get more water molecules into the gas phase, some of them will start to come back. And eventually, there will be as many molecules who are condensing as there are molecules that are evaporating. And this is our dynamic equilibrium. Vapor pressure then is a function of temperature and a function of the strength of intermolecular forces. So liquids with at high temperatures will have higher vapor pressures. You take that same liquid and cool it down, like we saw with the chart yesterday in water's vapor pressures. If you cool it down, then we get decreasing vapor pressure. If we decrease the strength of the intermolecular forces, so the forces that are holding those atoms and molecules together as a liquid, then we get a higher vapor pressure. If we have stronger intermolecular forces, then we get a lower vapor pressure. The vapor pressure, though, is independent of surface area because an increase in surface area at equilibrium will equally affect the rate of evaporation and the rate of condensation. So you have more space, you got a higher surface area, but as you increase that, that's more areas where your liquid can evaporate and more areas where your liquid can condense. The boiling point of a liquid is the temperature at which the vapor pressure of a liquid is equal to the pressure above it. At boiling point, the thermal energy is enough to cause the water molecules in the interior of the liquid to become gaseous, forming bubbles containing gaseous water molecules. So when the vapor pressure of your liquid reaches atmospheric pressure, in most cases, that is when water boils. So we're going to have a slide about this. If we don't, I'll mention it. I'll bring it up. Okay, so if the boiling point, the boiling point is the point at which atmospheric pressure is equal to, I always write so sideways, is equal to the vapor pressure. And we increase temperature, we increase vapor pressure. Once the boiling point of a liquid is reached, additional heating only causes more rapid boiling. It does not raise the temperature of the liquid above its boiling point. A mixture of boiling water and steam will always have a temperature of 100 degrees C at 1 atmosphere pressure. Only after all the water has been converted to steam can the temperature of steam rise beyond 100 degrees C. And this is because in your water, as soon as any water molecule hits this 100 degree point, hits the boiling point, or 100 degrees C at atmospheric pressure, it will then explode into gas. And those are the bubbles that we see forming. And so since every time you've converted your water at 100 degrees C into gas and it leaves, it'll never get above 100 degrees C. This is actually how the rice cookers work. So you have a rice cooker, there's got a little pot, there's just a switch on the front. And if you press that switch, it starts the rice cooker. And what happens is there's actually a magnet inside and a piece of metal that is calibrated to lose its magneticity. It's called the Curie point. It loses its ability to be magnetic just above the boiling point of water. So your rice pot that's sitting on your counter will continue to boil and boil and boil and boil until all of the water is gone. As soon as all the water is gone, the rice is done. This is a clever way that you can use the boiling point and the fact that boiling point doesn't change in a practical application. So this is an example of our heating curve during boiling. We have temperature of the liquid increasing up to the boiling point, and then it boils until all of the liquid is gone. And as soon as all the liquid's gone, that temperature is going to shoot right back up again. I don't know if we're going to talk about it. So one of the interesting things about boiling, right? We use boiling to cook pasta. The boiling point, if boiling point is dependent on atmospheric pressure, then water actually boils at a lower temperature at higher altitudes. So as we go up altitude, then our boiling point will go down, and it takes longer to cook spaghetti. So evaporation is an endothermic process. The system absorbs heat because energy is required to break molecules away from the liquid. Our bodies use the endothermic nature of evaporation for cooling. As the sweat evaporates, it absorbs heat from our bodies, cooling us down. A breeze intensifies the cooling effect. High humidity slows down the evaporation and prevents cooling. When the air already contains high amounts of water vapor, sweat does not evaporate as easily, making our cooling system less efficient. And this is why you say in Fresno that at least it's a dry heat. Because if it was somewhere like Florida or other places with high humidity, it's just miserable. Minnesota is like that. That high humidity reduces that cooling effect, and you can overheat very easily in hot, humid weather. Condensation, on the other hand, is an exothermic process. Heat is released when a gas condenses to a liquid. As steam condenses to a liquid on your skin, it releases heat and can cause severe burns. The exothermic nature of condensation is also the reason that overnight temperatures do not get as low when humidity is higher. Because as the temperature starts to come down, water starts to condense out of the air onto everything. It releases more heat, and it prevents the temperature from dropping further. Excuse me. The heat of vaporization, delta H vape, is the amount of heat required to vaporize 1 mole of liquid. The heat of vaporization of water at its normal boiling point of 100 degrees C is 40.7 kilojoules per mole. And delta H here is positive because vaporization is endothermic, so energy must be added to the water to vaporize it. Because chemical bonds and bonds between atoms and even these intermolecular forces are like energy sinks. They're made of energy. And so when you break those bonds, it takes energy to break those bonds. So you have to add water to vaporize and get past those bonds and break those bonds. So the same amount of heat is involved when 1 mole of gas condenses, but the heat is emitted rather than absorbed. Delta H is negative because condensation is exothermic. It's exothermic, so energy is given off as the water condenses. Remember that. So delta H is negative for exothermic processes. Negative delta H, exothermic. Whoops. Positive delta H, endothermic. We use the heater of vaporization to calculate the amount of heat energy required to vaporize a given amount of liquid. You can use the heat of vaporization as a conversion factor between moles of liquid and the amount of heat required to vaporize it. So for example, here we have things like water, which has a heat of vaporization of 40 kilojoules per mole. And then you'll notice that we have things like acetone and diethyl ether, which have much lower heats of vaporization. Because their intermolecular forces are weaker, you'll also notice that they have lower normal boiling points. Let's calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. So our first step here is to notice that our units of the heat of vaporization are per mole. So I have to take our 2.58 kilograms H2O, and we are going to first convert this to grams because our molecular masses are in grams per mole. So 1 kilogram is 1,000 grams. I'm going to use one of these. It's actually the way I prefer to do these stoichiometry problems. Well, I guess stoichiometry is specifically for chemical reaction equations. But we're going to first go from kilograms H2O to grams H2O. And then from grams H2O, we want to go to moles H2O. Right? So 1 mole, we want moles. 1 mole is about 18 grams. So once we have that, now we will have moles here in our next column, and we want to convert to kilojoules. And so we get 40.7 kilojoules. That's the unit we want. I wrote kilograms, but kilojoules per 1 mole H2O that we are boiling. So let's crunch the numbers. 2.58 times 1,000. I wrote 2.57. 2.58 times 1,000 times 40.7 divided by 18. And since I used 18, we're going to use two significant figures, and we're going to go 5.8 times 10 to the 3 kilojoules, which is a lot of energy. So 5.8 times 10 to the 3 kilojoules to vaporize this 2.58 kilograms of water. Now let's take a look. If we had a drop of water weighing 0.48 grams, right, 0.48 grams H2O, condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees C. If the heat released during the condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? And it's an aluminum block. Okay, so a little bit more complicated. Sorry, have to come back here. This is a negative. I know somebody's going to message me, or sorry, no, it's positive. Vaporization is endothermic. Exothermic? Sorry, no, we're talking about condenses here. Yeah. Okay, we're endothermic. No, I was right. Yeah, because it has to absorb this much energy to vaporize. Sorry for the confusion. Anyways, this problem really starts out the same way. We have this amount of water. We're eventually going to get to a Q equals MC delta T problem. You remember those? But we first need to know how much energy we are imparting to this aluminum block. So it's 0.48 grams of water. We need to convert to moles of water first. Again, we're just going to use 18 grams H2O for 1 mole H2O. When you do this on homeworks and other such, you should use more significant figures because you have them. Just doing this here for the sake of ease. So then we've converted there, and we know from our previous slide that it's 40.7 kilojoules per mole. 40.7 kilojoules per 1 mole. A negative, though, because we are condensing, and condensation is an exothermic process. And then we'll just calculate for the amount of energy that we are adding to the metal block. So 0.48 times a negative 40.7 divided by 18. And we are going to impart negative 1.09 kilojoules of energy. So our next step is to make a little room. always have to wiggle a little bit, otherwise Notability gets angry at me for some reason. Okay. Alright, so this is how everything builds on the next thing. So we first need to convert our kilojoules into joules. So, and because we're adding heat to our aluminum block. So if we're adding heat, this is going to be a positive Q, 1090 joules is equal to the mass of our aluminum block, 55 grams, the heat capacity of aluminum, right? So times 0.903 joules per gram degree C. Oops. I'm going to zoom now. And then our units there of, gosh, that's what I'm talking about. Our units of our heat capacity are in grams per degree, or joules per gram degree C. So that means we're going to continue to use temperature. So our temperature final minus our temperature initial, which is going to be 25 degrees C. And now we just do some math to solve. So 55 times 0.903, we get 49.665. We've multiplied grams by 1 over grams here, so we get joules per degree C, minus that 49.665 times 25 to get a negative 1,241.625. And here we're doing multiplying our joules per degree C by degree C, so we'll get joules per gram because we cancel out the degree C there, equals over here, we still have 1090 joules. I'm sorry, I left off the temperature final is in here. So then we're going to take our 1090 joules and we're going to divide by, oh sorry, we multiplied 55 times 0.903, so that canceled out grams, and then we multiplied by 25 degrees C, so that actually cancels out degrees C. So we've canceled out grams and degrees C, so our units on this number then are just joules. And so we'll do, is this going to work out right? We'll see if this works out right. We're going to do 1090 plus 1241.625 will give us 2331.625 equals 49.665 joules per degree C times temperature final. I feel like I'm missing something here. Then we'll take this number and we'll divide it by 49.665. Oh, that came out to be something fairly reasonable. 46.9, because we waited till the very end to round. 46.9 degrees C equals temperature final. Yeah, so we actually heated our block from 25 degrees C all the way up to 46.9 degrees C by adding that much energy. That's a lot. Because if we had had a negative 1,000, then we would have added, I'm just going to check something real quick. If we had made that a negative 1,090, then it would be 1241.625 minus 1090. And then that would have been divided by, so that wouldn't have made any sense, 49.665. That would have been only 3 degrees C. So that doesn't make any sense because we added heat instead of removing it. So yeah, this is our answer. If we had a half gram drop of water that condensed on the surface of a 55-gram aluminum block, and all of that energy went into it, it would increase from 25 degrees C all the way up to 46.9 degrees C. That's a lot of energy. That's a lot of heat. So, as the temperature of a solid increases, thermal energy causes the molecules and atoms composing the solid to vibrate faster. The melting point of a solid is when the atoms and molecules have had enough thermal energy to overcome their intermolecular forces that hold them at their stationary points and turn them into a liquid. The solid turns into a liquid because those intermolecular forces are no longer enough to hold together the atoms and molecules. When ice melts, those water molecules are breaking free from their solid structure to become liquid. As long as ice and water are both present, the temperature will be 0 degrees C. This is the same thing as when things are boiling. If you have at least one ice cube in your drink, that will stay at 0 degrees C until the ice cube melts. Why is this? It's because melting is an endothermic process. So a mixture of water and ice will always have a temperature of 0 degrees C at 1 atmosphere pressure. That's important. Only after all the ice is melted will additional heating raise the temperature of a liquid past 0 degrees C. Again, so it's very similar to our boiling curve. We have this melting curve. So as the temperature increases, we just keep increasing the temperature until some of it starts to melt. As that solid's melting, we're pouring more energy into melting than we can pour into heating the temperature or increasing the temperature. So the liquid and solid together stay the same temperature at 0 degrees C for water. And then as we increase past that, after we've melted everything, then the temperature can increase again, and eventually we'll get to boiling. Adding ice cools a drink because melting is endothermic. The melting ice absorbs heat from the liquid in the drink and cools the liquid. Melting is endothermic because energy is required to partially overcome the attractions between the molecules in the solid and free them into the liquid state. Freezing is exothermic. So if you take your water and you start freezing it, heat is released when a liquid freezes into the solid. And as water in your freezer turns to ice, it releases heat because freezing is exothermic. The energy release must be removed by the refrigeration system of the freezer. So it's constantly cooling when you put ice or water in there to freeze, to make ice cubes. This is called the heat of fusion, the amount of heat required to melt 1 mole of a solid. The heat of fusion for water is 6.02 kilojoules per mole. So it's a lot less than boiling, but still decently significant. So if we have delta H is positive, because where melting is endothermic, and energy must be added to the ice to melt it. That makes sense too, right? If you don't put it into the freezer to melt it, you add heat to melt it. You add heat to your frozen, pork chops or chicken or whatever, frozen vegetables to thaw them. The same amount of heat is involved when 1 mole of liquid water freezes, but the heat is emitted rather than absorbed. Delta H is negative because freezing is exothermic. The energy is given off as the water freezes. And we can use the heat of fusion then to calculate the amount of heat required to melt a given amount of a solid. Use the heat of fusion as a conversion factor between the moles of a solid and the amount of heat required to melt them. So just like we did for heat of vaporization, we're just doing that now for heat of fusion. So if we have a 15.5 gram ice cube, right? Again, this is a unit conversion problem. And, right, so the heat of fusion is negative 6.02 kilojoules. Sorry, this is for fusion. This is for freezing, and we are currently melting. So we're going to have a positive value. So it's 6.0, I'm so sorry, 6.02 kilojoules per 1 mole. So we want the moles, or we want to convert to moles first so that we can use this. Again, 18 grams of water is 1 mole of water. And then we're going to go from 1 mole of water, or from our moles of water, really. So we went from grams to moles to kilojoules next. 1 mole is 6.02 kilojoules of energy, heat energy, thermal energy. 15.5 times 6.02 equals that, divided by 18. We get 5.2 kilojoules. So it's 5.2 kilojoules being absorbed, because it's the positive value, being absorbed into the water to melt the ice cube. The heating curve for ice. Oh, sorry, this is the heating curve for ice beginning at negative 25 degrees C and ending at 125 degrees C. Let's go through and name these points. So we got some important points here. We have I here, this first one, right? So we've gone from negative 25 up to 0. And then as we go up to 0, we're going to pass 0 and continue up. So that means that this is melting. Right, so melting. Oh, sorry, the correct states of water. So we've got solid, liquid, in between solid and our last one. So we've reached 100 degrees C. That's the boiling point of water. And so that's going to be our gas. Another kind of question that would be asked on an exam. What is the state of water, H2O, at a given temperature? Hopefully not a hard question. So let's see what happens. And this is going back now to our Q equals mc delta T. Going back to that a little bit, let's calculate the amount of heat in kilojoules needed to convert 1 mole of ice at negative 25 degrees C to water at 37 degrees C. This question is a little bit tricky. And you have to remember that we're going to have this curve. And so we're starting at negative 25 degrees C. We're going to go up to 0 degrees C. And once we reach 0 degrees C, our equation changes. Because here now, instead of using our Q equals mc delta T, we're going to use our heat, our delta H of fusion, to calculate how much energy is going to be required to melt our solid water, or ice. And from there then, we're going to use Q equals mc delta T again. Q equals mc delta T again to get from 0 degrees C all the way up to 37 degrees C. The easiest way to get tripped up on this is to call 37 degrees C your temperature final, negative 25 degrees C your temperature initial, and just use Q equals mc delta T all the way through. It does not work that way. What we can do, though, is we can say, no, we can't, because the delta, this is the specific heat of ice. Specific heat of ice is different than that of water. So we're actually going to have 3 steps to this problem. We're going to have Q, right? So we're calculating Q equals M. We have 1 mole of ice. Now we actually need to convert that 1 mole to grams. So it's just water. So 1 mole, or I should do this the other way because that's 18 grams is 1 mole of H2O. So if we have 1 mole, we have 18 grams. So I'm going to put 18 grams here. And this is going to be ice. We're going to do another one for, actually we'll do them in order. We'll do the delta H of fusion next. And then we'll do water, heating of the water. So 18 times 2.09 joules per gram degree C. And then our temperature change is going to be from, our T final will be 0 minus a negative 25 degrees C. Makes sense so far? So then we have delta H of fusion, and that's actually simpler. So our delta H of fusion, Q, is going to be equal to, and remember, melting, we have to add heat to melt water. So it's an endothermic process. So we're going to use a positive 6.02 kilojoules. Kilojoules per mole. And we have 1 mole of water, or ice. I guess I'll put H2O here. And that 1 mole, or 18 grams, those are interchangeable, and that's not going to change as we go from negative 25 all the way to 37. Our next part here then is for heating water after we've melted it all. And again, that's going to be 18 grams times, now it's 4.184 joules per gram degree C, times our new temperature final and temperature initial. So going from 37 degrees C will be our temperature final, minus our temperature initial, which is 0 degrees C. So we just calculate for each of these. Starting at the top one there, 18 times 2.09 times a negative, or sorry, we're subtracting a negative, so positive 25. And we're going to get, let me write it like this. So our Q total is going to be Q ice plus delta H fusion plus Q water. Just to give them general names. And this is going to be 940.5 joules. For our next one, we're going to do 6.02 times 1. So we're going to get 6.02, but it's very important here to note what are our units. We've got kilojoules. The rest of our numbers are in joules, so we're going to convert this one into joules as well. And to do that, we simply multiply by 1,000, so we're going to get 6,020 joules. All right, so we added that in our delta H of fusion. And then for water, it's 18 times 4.184. All right, that's this part here. And then times 37 minus 0, so it's just 37. And we're going to get 2,786.544 joules. And now we'll calculate our Q total. Will be that 2,867 plus 6,020 plus 940.5 for a total of, and now let's consider our significant figures here, significant digits. 6,020. Oh, I really should have written this in scientific notation. This should be 6.02 times 10 to the 3. Three significant figures there. 2 decimal places. We also have three decimal places and 1 decimal place, so we're going to use 1 decimal place because we're adding. When you add or subtract, use the number of decimal places. And so we'll get 9,747 joules to increase our temperature from to increase the temperature of the water to go from negative 25 degrees C ice all the way up to 37-degree water. They take 9,747 joules. So you always got to remember that there's this step in between. You cannot just go from all the way from one end of the spectrum to the other. Sublimation then is a special physical change, a rare one that we don't see very often, and that's going from a solid state directly to the gaseous state. When a substance sublimes, the molecules leave the surface of the solid, where they are held less tightly than the interior, and become gaseous. Dry ice is the one example I think that we know of and see in day-to-day life. Maybe not every day, but on special occasions. Carbon dioxide does not melt at atmospheric pressure. At any temperature. It doesn't matter what the temperature is, it does not melt at atmospheric pressure. At negative 78 degrees C, the CO2 molecules have enough energy to leave the surface of the dry ice and become gas. Dry ice is solid carbon dioxide. The solid does not melt, but rather sublimes. So it goes straight from this solid into a gas. You know that regular ice actually will sublime at temperatures below 0 degrees C. In cold climates, ice or snow lying on the ground gradually disappears, even if the temperature remains below 0. It's sublimation. Similarly, ice cubes left in the freezer for a long time slowly become smaller, even though the freezer is always below 0 degrees C. And so this is one that we're maybe not as familiar with, but it does occur. If you've ever left ice cubes in the freezer for a long time, I have before, and come back and wonder, why are they so small? This is why. Ice also sublimes out of frozen foods. The ice crystals that form in the bag are water that is sublimed out of the food and redeposited on the surface of the bag. Foods that is frozen for too long becomes dried out because of this sublimation process. You can deep freeze foods, taking them farther into colder temperatures, and you can avoid this sublimation problem and the drying out of food. The colder temperature lowers the rate of sublimation and keeps that food good longer. So now we're going to transition here a little bit, and we're going to talk about these intermolecular forces that we've been mentioning so much. These intermolecular forces are electrostatic forces of attraction between molecules. The strength of the intermolecular forces determines the state, solid, liquid, or gas, of the substance at room temperature. So we've already mentioned this, but strong intermolecular forces result in liquids and solids, tend to, with high melting and boiling points, and weak intermolecular forces tend to result in gases, with low melting and boiling points. The first intermolecular force that we're going to talk about is dispersion force, also called the London force, sometimes called the London dispersion force, if you want to throw it all in together. Dispersion forces are caused by fluctuations in electron distribution within molecules or atoms. Since all atoms and molecules have electrons, all substances have dispersion forces. The electrons in an atom or molecule at any one instant may be unevenly distributed. You can kind of think of this like if you got a water bottle and it's not completely full, and you turn it on its side, and you're sort of walking with that water bottle. The water inside shifts from side to side, it moves around. In that case, it's being affected by you moving it. But if you have these atoms or molecules that are moving around, and they bump into each other, that close touch of those electronic fields will force the electrons to the other side. And so as these electrons or these molecules and atoms are moving around together, those electrons... Oh, wow, that was terrible. So we've got this here. Let's say this is like our electrons. Now I'm just going to copy this. Paste. Oh, pasted image. Undo that. So we've got these guys in here, like this. These electronic fields are going to shift out away. This guy might shift down this way. This one's going to shift up this way. And so they're constantly going to be in this sort of state of flux. And you get these very, very slight differences in polarity. So for example, here we'd have a slight positive on this side to that side. We'd have a slight positive going this way. Slight positive going this way. Very, very slight. But those are enough to cause the molecules to bunch up and, in some cases, stick together. So we're going to look at this too. So we've got the electrons around this helium atom creating these instantaneous dipoles. So in frame 1, they're roughly on either side. Here again, either side. But in this third frame, the electrons have both moved over to the same side. And because of that, you get this dipole moment. Very, very temporary. Very instantaneous. But it's enough. And that's what these London dispersion or London forces or dispersion forces are called. Or are caused by. And this occurs in everything. So if you get instantaneous dipole in any one helium atom, it induces an instantaneous dipole on the neighboring atoms. You can see how we've moved these electrons here. They've all moved over to the left side. And those weak attractions then in between here are caused by the electrons shifting over to the opposite side of the atom. The electrons shifting over. The dispersion force occurs as neighboring atoms attract one another. The positive end of one instantaneous dipole attracts the negative end of another, and they fluctuate around like this. The dipoles responsible for the dispersion force are transient. So they're constantly appearing and disappearing in response to fluctuations in electron clouds. The magnitude of the dispersion force depends on how easily the electrons in the atom or molecule can polarize in response to an instantaneous dipole, which depends on the size of the electron cloud. A larger electron cloud is more easily polarized. Molar mass alone does not determine the magnitude of dispersion forces, but it can be used as a guide. So if we add more molar mass, adding more protons and neutrons, you're also adding more electrons and bigger molecules or bigger elements. And so within a family, as you get bigger, you have bigger cloud of electrons, and they can be more easily polarized and have more of these dispersion forces. So this is the molar mass and the boiling point of the noble gases. And you can see that as we go down, as they get bigger, as we move from... just write it over here. As we move from... N, right, our principal quantum shells, principal number. N is the principal quantum number which corresponds to the shell. As we go from N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, each of these are getting bigger as we move down. And so as we get bigger and bigger, it's more easy to polarize those electron clouds, which gives us higher boiling points. Now, albeit these are still very low, that's 165 Kelvin, that's incredibly cold, but still much higher than the 4.2 Kelvin of helium. So which hydrocarbon then of these two has the higher boiling point? Is it going to be CH4 or is it going to be C2H6? C2H6, so CH4, let's draw CH4. then C2H6 is going to have a much larger electron cloud, roughly twice the size. And so because we have this much larger area of electrons, that's going to be more easily polarized. And so C2H6 is going to have a higher boiling point because it's going to have stronger intermolecular forces. Our next intermolecular force is the dipole force, the dipole-dipole. This exists in all polar molecules. Polar molecules have permanent dipoles. The dipole-dipole force is the attraction between the positive end of one permanent dipole and the negative end of another. All molecules have dispersion forces, but in addition to those dispersion forces, polar molecules also have dipole forces. So polar molecules in general have higher melting and boiling points relative to nonpolar molecules of similar molar mass because they have an additional force working to hold those molecules together. So we talked about polarity again, and that's when you have this uneven distribution of really electronegativity. So oxygen here is much more electronegative, we'll use blue for electronegative, than hydrogens or even carbon. And because this is a trigonal planar, because we have 3 bonding groups and we have 0 lone pairs, because of this, we get this uneven symmetry, or a lack of symmetry, asymmetry. And then the positive end of one of these can line up with the negative end of another, and so on and so forth, to have really strong intermolecular forces and hold them together. The effect of polarity on melting and boiling points for 2 compounds of similar masses are shown here below. And we have formaldehyde and ethane. Right? So same molar mass almost. But the boiling point of formaldehyde is negative 19.5, whereas for ethane it's negative 88. So it's 68 almost, or just over 68 degrees Celsius different. And the melting point is even more dramatic, or I guess is a little less dramatic. It's larger, but it's also only double. But you can see that this dipole-dipole force adds a lot of strength to the intermolecular forces, causing them to have higher boiling points. The polarity of molecules also affects its miscibility. So we talked about oil and water and why they don't mix. Part of that is because of these dipole-dipole forces. So miscibility is the ability of a liquid to mix with another liquid without separating into 2 phases. In general, polar liquids are miscible with other polar liquids, but are not miscible or immiscible with nonpolar liquids. This gives rise to the term like dissolves like. Oily hands or oily stains on clothes can't be washed with plain water. That's why we have soap. And we talked about what soap is. It's got a little polar end on it, and then a long nonpolar chain that is able to interact with both phases and pulls away the oil molecules. So polar and nonpolar compounds are generally not miscible. Pentane does not mix with water. As we're seeing here, it's not super clear, but we have pentane on top, water on the bottom. We have oil and vinegar in salad dressing, right? Because the vinegar is water and the oil it's an oil, it's nonpolar. Or something like a tragic oil spill from a tanker. You can see these big oil slicks that form on the surface of the water. Kind of hard to see there at the bottom, but it stays on the surface, and then it spreads out for miles and miles. And it's incredibly hard to clean, and it gets everywhere. So, a couple methods here for how to determine if a molecule is polar. The Book's method is to determine whether the molecule contains polar bonds. Right? So if we have a bond like, well, carbon and oxygen would be a polar covalent bond. And then we determine whether the polar bonds add together to form a net dipole moment. Or we have Mrs. K's method, a little bit simpler, and we just check to see if there are lone pairs on the central atom. And this is, of course, most of the time, but a molecule is nonpolar if both conditions are true. There are no lone pairs on the atom, central atom, and the atoms bonded to the central atom are identical or have the same electronegativity. So if one of these is false, then we're polar. Polar if either is false. Nonpolar if both are true. Polar if either is false. So, this is carbon tetraiodide. This is not a great font. I'm considering changing it already. We need a font with serifs. Okay, so let's take a look. Right, we're gonna draw the Lewis structures. So we've got carbon, and we've got 4 iodine atoms. And those are all going to be bonded here. Iodine is a halogen, so it's going to have 7 electrons. So we're going to do 7 E times 4, and we're going to add that to carbon's own 4 electrons times 1, right? So we get 28 plus 4. So 28 plus 4 is 32. So we've already used 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Sorry, counted 1 for the bonds. Okay, so we've got all of these. We look and we see that we have 4 bonding groups and we have 0 lone pairs on our central atom. And since all of these bonds are the same, we then have a tetrahedral, and we're going to be nonpolar, and therefore no dipole forces. Dipole, dipole. CH3, carbon, we're going to put a chlorine here, and then we're going to put a hydrogen here, and a hydrogen here, hydrogen here. And we're going to say that H, right, has 1 electron, C has 4 electrons, and chlorine has 7 electrons. So we have a total of 12 electrons. So we've already have 8, 9, 10, 11, 12, 13, 14. Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, right, times 3. So we have 14 electrons. Okay. Again, though, first thing to check, we have 4 bonding groups and 0 lone pairs, but let's take a look at our Mr. K's rules. The atoms bonded to the central atom are identical or have the same electronegativity. This is false. Chlorine has a much greater electronegativity than hydrogen. And so what we have here then are dipole, dipole, dipole. It's like if Little Caesar did chemistry instead of pizza. Instead of pizza, pizza, it's dipole, dipole. HCl is a little simpler. We don't have to go even so far as to draw out the entire Lewis structure because we just have the 2. We also notice that if we're to look at Mrs. K's rules, there are no lone pairs on the central atom. That's false. So this is polar. We have lots of lone pairs. And so this is then also going to have dipole, dipole. I need to mute my notifications, it would seem. I'm being bombarded. Okay. So again, you can just check lone pairs on the central atom or not. Polar molecules. Oh, sorry. One last type of bonding, or maybe this isn't the last type of bonding. Polar molecules containing hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen exhibit an additional intermolecular force called a hydrogen bond. The hydrogen bond is a sort of super dipole-dipole force. And it happens when there's a large electronegativity difference between hydrogen and these electronegative elements, fluorine, oxygen, and nitrogen. And it's only for those ones. Not sure if you can hear the dogs barking. Somebody just set off a firework. The small size of these atoms allows neighboring molecules to get very close. And because of that closeness, they form a sort of pseudo bond, almost an ionic bond in strength. So hydrogen bonds are not covalent bonds. Hydrogen bonds occur between molecules. Covalent bonds occur between atoms within the same molecule. So hydrogen bonds are much weaker than covalent bonds. 2 to 5% the strength of a typical covalent bond, but still much stronger than your London dispersion forces. So in hydrofluoric acid, the hydrogen on each molecule is strongly attracted to the fluorine on its neighbor. The intermolecular attraction of a hydrogen atom to an electronegative atom is called a hydrogen bond. Again, we have fluorine, oxygen, nitrogen. These are the three atoms that can combine with hydrogen to make these hydrogen bonds. Since methanol contains hydrogen atoms directly bonded to oxygen, methanol molecules form hydrogen bonds to one another. The hydrogen atom on each methanol molecule is attracted to the oxygen atom of its neighbor. So in addition to our London dispersion forces, you also get this hydrogen bond. The effect of hydrogen bonding on melting and boiling points for two compounds of similar molar mass are shown here, the methanol and ethane. We looked at ethane before, right? Negative 88. Well, the boiling point for methanol is 64. There's a huge difference in intermolecular strength between just London dispersion forces and hydrogen bonding. And you can see the melting point is greatly different too. Water molecules form strong hydrogen bonds with one another, which is why the boiling point of water is 100 degrees C, which is remarkably high for a molecule with such a low mass. And we just saw that boiling point of methanol with a mass of 32, right, getting close to twice the size of water, is only 64 degrees C. These are especially strong hydrogen bonds. The two strands of DNA are also bonded together using hydrogen bonds. So we get thiamine, adenine, cysteine, cytosine, and guanine forming these. Again, so these red ones are oxygen, and we have a nitrogen, and we also have nitrogen here, hydrogen. Sorry, I meant to say that the white one was hydrogen. Hydrogen then attached to a nitrogen with this other oxygen. We form these hydrogen bonds to hold our DNA together. So our very lives depend on hydrogen bonding. So which of these two has a higher boiling point? Hydrofluoric acid or hydrochloric acid? You can take a hint from which chapter we're on, what we're working on currently, that hydrogen forms hydrogen bonds when it's attached to fluorine, oxygen, and nitrogen. So fluorine, then, hydrofluoric acid, is going to have the higher boiling point. So, what affects boiling point? Boiling point goes up as our intermolecular forces go up. Because it's holding, the more that the atoms or the molecules want to hold together, the stronger the force is holding them together, the harder it is going to be to break those bonds, the more energy that it's going to take to break those bonds or those forces, and then the higher the boiling point. The ion dipole force is another intermolecular force that occurs in mixtures of ionic compounds and polar compounds. This is especially important in aqueous solutions of ionic compounds. So we have sodium chloride dissolved in water. The negative chloride ions interact with the positive poles of the water. So you get the negative chloride interacting with the positive poles of the water, and the positive sodium ions interacting with the negative poles of the water molecules. Take a step back. This is partly why sodium chloride dissolves in water. It is because the water gets in and it separates the sodium ions and the chlorine ions and isolates them. So, quick summary of our intermolecular forces. We have dispersion force, or London forces, and that's where we have the electron clouds shifting around back and forth, creating instantaneous dipoles and inducing instantaneous dipoles in the molecules around them. And this occurs in all atoms and molecules. And then increasing in strength, we have dipole-dipole forces, which only occur in polar molecules. And those are moderate strength, relative strength. We have the hydrogen bond, which is strong, and that only occurs in molecules containing hydrogen directly bonded to fluorine, oxygen, or nitrogen. And then we have ion dipole bonds, which are very strong. And that's where we have mixtures of ionic compounds and polar compounds. And you get this you get a circle of the polar around the inner ionic compound. Those are our intermolecular forces. Let's take a look now at some, just very briefly, just a few more slides here. We've got different types of solids. So we've talked about very early on how we can have crystalline solids, which have a well-ordered array of atoms or molecules, or we can have amorphous solids, which have no long-range order. Crystalline solids can be divided into three categories based on the individual units that compose the solid. We can have molecular crystalline solids, ionic crystalline solids, or atomic crystalline solids. For our molecular crystalline solids, the component units are molecules. And so we've got component molecules occurring in these long-range ordered sort of patterns, like ice. Right? We have all these water molecules coming together to form a crystal. We have crystalline ionic solids, which the component units are formula units of cations and anions, right? So we have table salt, which is sodium chloride, and that's a formula unit. Because when you look at table salt as a whole, there's no single sodium chloride molecules. We just have this repeating array of sodium and chlorine, and so we use formula units. We also have atomic crystalline solids, and they can have variable melting points. Sorry, I didn't mention for the other ones, low melting points for molecular solids. Again, why ice is a good example. High melting points for things like table salt. Very, very high melting points for ionic solids. And then variable melting points for atomic solids. Right? You can think of something like mercury, which has a melting point of like lower than room temperature, so it occurs as a liquid. Our molecular solids are solids whose component units are molecules. Ice, or dry ice, being solid H2O, solid CO2. They're held together by their intermolecular forces, which can be dispersion forces, dipole-dipole forces, and hydrogen bonding. Ice is held together by hydrogen bonds, and dry ice is held together by dispersion forces. And that's why you observe such a huge difference in their melting points. They tend to have low to moderately low melting points, right? So ice at 0 degrees C and dry ice at negative 78 degrees C. The ionic solids are solids composed of formula units, the smallest electrically neutral collection of ions that compose a compound, right? So table salt, calcium fluoride. They're held together by the electrostatic attractions between the cations and anions, or their ionic bonds. Sodium cations and chlorine anions are held together in a three-dimensional array. Very, very high melting points because those ionic bonds are so strong. So sodium chloride melts at a temperature of 801 degrees C. That's hot. I think that's hotter than glass melts. Soft glass melts. All right, atomic solids are solids whose composite units are individual atoms. Diamonds are one that we're very familiar with. You may not have known it, but iron actually forms an atomic solid. Or, sorry, I was thinking of a crystalline solid. And atomic solids, and then there's a solid xenon as well. Atomic solids can be divided into three categories, each held together by a different kind of force. And so they have very widely differing melting points. So we have our covalent atomic solids, we have our non-bonding atomic solids, and we have our metallic atomic solids. Those with covalent bonds, covalent bonds are very, very strong. They have very high melting points. Non-bonding are held together by dispersion forces. So just the instantaneous sort of transient shifts in electronic fields around them. They have very low melting points. And then we have metallic, which are held together by metallic bonds, and they have variable melting points. Again, mercury is a liquid at room temperature. But then you can have something like iridium, which has an incredibly high melting point. I think the highest melting point, maybe it's osmium, has a higher melting point of the elements. So covalent atomic solids are held together by covalent bonds, for example, diamond. And in a diamond, which is just pure carbon, each carbon forms 4 covalent bonds with 4 other carbon atoms in a tetrahedral geometry. A diamond crystal can be thought of as a giant molecule. Melting points are very high due to strong covalent bonds, and a diamond is estimated to melt at about 3,800 degrees C. I believe that's estimated because it's hard to do in the absence of oxygen, where it would burn. And this is an example. So this is what this tetrahedral structure looks like, and I'll try and highlight some of these. All right, so we have a tetrahedral. Oh, let's not use that color. There's a tetrahedral here. See that? There's a tetrahedral here. There's another one here. So each of these is forming a tetrahedral. And that's where you get these hexagons as well. So if we look at these atoms around this barrier, we have a hexagon. So it's that three-dimensional hexagonal pattern made up of tetrahedrals. Our non-bonding atomic solids are things like solid xenon, which are just held together by relatively weak dispersion forces. Xenon atoms have stable electron configurations and therefore do not form covalent bonds with each other. They already have 8 electrons, so they don't want to form covalent bonds. And they have very low melting points, where xenon melts at about negative 112 degrees C. Metallic atomic solids are held together by metallic bonds. And just in the simplest model, this consists of positively charged ions in a sea of electrons. So we've got all these positively charged nuclei. We're all just kind of hanging out near each other. And then the electrons are just awash around them. This also explains why metals have or metals conduct electricity. So metal atomic salts have variable melting points because metallic bond strength varies so much. Mercury being, like I've mentioned a couple times now, negative 39 degrees C, but iron melts at 1,809 degrees C. All right, so our simplest, we have each metal donating one or more electrons to this electron C. And the metal consists of the metal cations and a negatively charged electron C. So they're just all kind of in there together. The positive nuclei aren't moving around, but the electrons are shared and interchanged between all of the metal atoms. So let's take a look at some molecules and try and identify whether or not they are molecular, ionic, or atomic. So, NH3, we don't have an ion, so we can't have an ionic, or we don't have a metal, so we can't have an ionic bond. We have more than one atom, so this is a molecular. And then for calcium oxide, we know calcium's a metal, bonded to a nonmetal, so that's ionic. We know it's not atomic because we have more than one element. And then krypton is atomic. So when you're looking at any molecule or atom and you're trying to determine if that solid is molecular, ionic, or atomic, you should start with, well, is it atomic? Whoops. If the answer to that is no, then you say, is it ionic? If the answer to that is no, then it's molecular. So very simple sort of decision tree to make those determinations. Water is a very special molecule. It has a low molecular mass or molar mass, yet it is a liquid instead of a gas at room temperature. And that is because of its hydrogen bonding. So you look at the boiling point of atoms that are two hydrogens plus something else. You look hydrogen or oxygen here at the top has a boiling point of 100 degrees C, but then hydrogen sulfide is at negative 100 almost, somewhere in between there, maybe negative 80. Hydrogen selenium, or selenium hydride, I suppose, is just a little bit higher than that, and tellurium hydride is just a little bit higher than that. And so you can see that water really is a special molecule in that it has such a high boiling point. Water's high polarity also allows it to dissolve many other polar and ionic compounds. As we saw before, it can surround those cations with either its positive or negative end because it's polar and isolate them from other ions. Water is the main solvent of living organisms. We use it in our bodies to transport nutrients and other important components throughout the body. And it also transports ions and charges and all kinds of things all over the earth. So where water exists, liquid water exists, life exists. And that's why we think that the evidence of water on Mars could suggest that there might have been or could still be life there. Also, Titan, I believe, one of Jupiter's moons, is made almost entirely of water. It's icy on the surface, but the strong magnetic forces from Jupiter actually keep the inside of it liquid. So it might have, and I believe there's a NASA mission planned to go there, to see what's under the surface of the ice, see if there's life there. The way water freezes is also unique. Instead of contracting, most substances contract when they freeze. Water actually expands upon freezing. And this is what makes ice less dense than liquid water. Because it's the same amount of mass, it's increased its volume though. So ice cubes and icebergs float. And water actually reaches its maximum density at about 4 degrees C. So the frozen layer of ice at the surface of Winter Lake actually insulates the water in the lake underneath from further freezing. If that ice were to sink, then it would allow the lake to freeze solid, and that would basically kill all aquatic life in these lakes that could freeze. The expansion of water upon freezing is one reason that most organisms do not survive freezing, actually. So that's why we don't have like cryo cells. I don't know if any of you have watched Futurama, but he gets frozen at the beginning of Futurama, and that's how he ends up in the future. There are some celebrities, I believe Walt Disney has been frozen, in hopes that someday we will overcome this problem of water expanding, freezing and expanding and rupturing the cell. And this is also why many foods, especially those with high water content, don't survive freezing well, because it destroys the internal structure. Flash freezing of fruits and vegetables happens so rapidly that it actually prevents the water molecules from aligning into their expanded phase, and so the cells aren't ruptured. You might have also had liquid nitrogen ice cream. Liquid nitrogen ice cream is especially smooth. There's a place called Creamistry. I think there might be one in Fresno. I know there's one in Bakersfield. But they use liquid nitrogen to freeze the ice cream. And they make it right there in front of you. It's really cool. There's a huge cloud of condensing water because the liquid nitrogen is so cold. But it creates this really, really smooth texture for your ice cream because it doesn't allow the water molecules to crystallize. Or they form very, very small crystals. Okay, so that is it for this chapter. What is this chapter? Chapter 12, Liquid Solids and Intermolecular Forces. Again, feel free to, contact me at any time. If I'm available, I will respond. Usually available. The test, again, is on Friday. And you'll have, starting at noon until 6 p.m. on Saturday. Please do not start the test too close to 6 p.m. because then I have to be watching, and if I'm not watching, you'll run out of time because the test won't be accepted after that. Okay, with that, I will sign off. Have a good one.